the change in liquid height over time. And we also use dm over dt to see based on the change in pressure over time. So this is for the gas or vapor system. So from mass balance, M, we correlate with the molecular weight and also number of mole, mass over mole. And then this molecular weight and number of mole is based on PV over nRT. So we have PV over RT. So this lesson will focus more once we goes into our system later. So the use for mass balance, in the end, we want to simplify until we have dH over dt. For liquid system and for gas system, we are going to simplify it until we have the change in pressure over time. Same goes for the mole balance within conservative principles. So the change in number of mole over time is equal to summation of rate of mole coming in minus summation of rate of mole coming out into our system. And we also have the rate of that component being generated. So I should specify that this is a specific number of component for species I. Let me put an I here so we can focus on a very specific component. And for N generation here is only valid for reactive system. So this is our general mole balance. Where do we use this for? So we use for a reactive system. We have reactors part of the lesson. So this will be using this quite a lot. And the second one is when we have a separation. So we use this mole because all the reaction and the separation mechanism is derived based on the number of mole. That's why we need to use the number of mole within the system. So basically from this, we can have for reactive system, normally we want to see the change in concentration over time. Or for separation system, the change in the mole fraction over time, whether it dx dt for liquid or dy dt for gas phase. So that is for the mole balance. And for energy balance, this is where we go a bit more complicated here. So we have the change in energy. So let's focus. The change in energy inside our system is represented by dmH. Keep in mind that the H here would represent enthalpy. So the change in energy inside our system is equal to summation of mass flow rate in together with its enthalpy minus summation of mass flow rate goes out together with its enthalpy. And if we have a reactive system, we need to include heat of reaction. And when we, if we are supplying heat, we also need to add on the term Q. And when we have the work supplied to our system, we also use the term of W. So now this part is all in rate form. So this energy balance, typically we are to simplify it until we have, it shows us the change in temperature over time. So that is the three conservative principle that we'll be using extensively in the modeling of our process. So the last recap for previous chapter is about the chain rule in ODE. So when you have the differential here, duv over dt, so this shows us that both u and v is changes with time. So basically the changes in u and v over time is also equal to the change in u over time at a constant v, plus the change in v over time at a constant u. So this chain rule we are going to apply for all mole and mass balance here in order to simplify our process even more. So, okay. So this is the lesson from the previous lecture. Keep in mind, start with all three here for any process. And then you are to simplify until you have all the variables that so that you can solve that equation later. And we're also going to use the chain rule in order to help us simplify our process model. Okay, good for the recap version. So if it's okay, give me a thumbs up so I can see. Okay, I can see one person thumbs up. What about others? Shall we move on to the today's lesson? So give me one round of thumbs up. So I cannot see the thumbs up. So I'm guessing it still takes some time to understand this. But let's move on to today's lecture. Give me a moment for my computer to cooperate with me. Moment. This is my computer is not cooperating. Okay. Okay, so this is what we have learned so far. And today the focus is on the modeling of the mechanical process. So the outline of today's lecture, the first part we are going to focus on pressure drop in processes. So what is pressure drop and why we need to take this into consideration. Once we understand about pressure drop, we are going to move into pump for liquid transfer, and the modeling will be focused on the pump power calculation. So once we settle on the pump, we'll jump into compressor system. So in the compressor system, we are going to focus on modeling towards compression power for both isentropic and polytropic compressor. Then we will focus our attention on the multi-stage compressor. So this would be our lesson for today. So this is still part of our course learning outcome, the first course learning outcome. So about the fluid transport. So normally we have a feed line and we have a reaction line and a separation line, reaction separation. So all of those things involving transporting a fluid from point A to point B. So fluid, let's recall what is the definition of fluid. So fluids can be either gas, liquid, or a mixture, or the mixture of these two. So it's still acting up again. Okay. I'm sorry, this is my computer is acting up. Maybe I should escape from this full screen. Okay, so fluid transport. So fluid is liquid and also gas. Liquid and also gas. And normally, without any work supply for us to transport from point A to point B, we need to use water tank, for example. So in this case, let me make this one like this so that I can still use my pen. Okay. So if you recall, for a fluid transport, normally for any residential area, we would have a water tank at elevated position, and we have a house here. So this difference in elevation, either delta Z or delta H, this would make the fluid to be transport possible. So what happened? So this fluid transport is based on the difference in height. So if you still recall about potential energy, the change in height will induce the potential energy in terms of rho GH. So this is rho GH. So this would happen instantaneously. So now, what about for us to transport into our water tank here? Do we need to supply in higher position water? So normally, for us to transport water into this liquid tank, we would need to put some work. So this work, we are supplying it in terms of pump. So keep in mind that over here at this location, we also have the delta P. So how much work we should supply to our pump so that it can put the water inside our tank? So we should supply work more than our delta P, or to put it simply, work to overcome our delta P here, to overcome the pressure difference. So for liquid, to overcome this pressure drop, we have a rotating equipment called pump, whereas for gas, we use compressor. So this is the two types of the mechanical equipment that we are going to focus on today. So now let's get back into our previous process for biodiesel production. So if you notice here, there is a lot of pump being put in here. So which means we need to supply the energy so that fluid can be transported through this pipeline until we can make our process a success. So all this pump, all of this equipment, whether being it a pipeline, heat exchanger, reactors, everything shows here they would have a pressure drop. And we have delta P of heat exchanger, delta P of reactor, delta P of tank, which means we need to supply work more than all of this delta P combined. So for aside from this specific equipment, for specific equipment, pressure drop by specific equipment, we also have pressure drop by the pipe itself and also pipe fittings. So any type of fittings, we will have induced some pressure drop. So the first part of today's lecture will be focusing on the pressure drop. So for pressure drop of a process, typically for the gas phase reactor, we can expect pressure drop up until 10% of the inlet reactor, because for the gas phase reactor, it's all flowing into much smaller pipe, multiple smaller pipe. That's why the change in the diameter will induce some pressure drop. We also have a packed bag reactor where there is a tube containing catalyst. So the gas or the fluid will have to overcome, maneuver through all of that catalyst. So it will also induce pressure drop more than 0.5 bar. For fluidized bed reactor, we have a laser pressure drop. For heat exchanger, similar to gas phase reactor, because from the pipeline, this big pipeline will be transferred into smaller multiple tube that will induce the pressure drop. So another part is in term of pipe and fitting. So let's goes into one by one. So when we have a pipe, there will be bend inside the within the pipeline. So all of this bend will induce this pressure drop. So we are going to take that into consideration also. We also have in term of reduction from flow reduction. So basically we have from the tank, from big tank here, so to be the fluid to be transported into smaller pipe. This would induce a phenomena pressure drop we call as a reduction, and vice versa. So from the pipe goes into our tank where there's sudden expansion, that also would induce the pressure drop. So the next part is about valve and orifice plates. So in any process, we have isolation valve, basically for servicing. We also have control valve. That one we have a control so that we can maintain a certain flow rate. And we also have this orifice plate. This orifice plate typically is used to measure the flow rate within the pipeline. So all of this would induce pressure drop inside our process. So how do we know when to use, how do we define the pressure drop? So let's go into the next slide. All of this delta P, the delta P, typically we call it as head, the head loss within our system. So let's say we have a liquid transmission. Where does the head loss happen? The first one is the sudden contraction from the feed to the vessel into the pipeline. And we also have, for valve, we would have an isolation valve. So that pressure drop from this valve, we should also take into consideration. We also have 2 isolation valve and 1 check valve for pump, orifice plate for measure the flow, a control valve, isolation valve for the control valve, for pipe band, and the isolation valve for discharge vessel, and then the sudden expansion for the fluid entering the discharge vessel. So let's do some exercise so that we can appreciate where does this head loss come into place. So for the first exercise, let's say we have a liquid is to be transported from tank 1 into tank 2 using a pump. So by using the previous guideline and your understanding by referring the previous two slides, identify the valve required for this process, typically required for this process. So refer to this diagram together with these slides. Try to understand where does this head loss would happen. In the meantime, let me try to draw this. So this would be our diagram here. So let's refer to the previous slide so that we can identify valve for our process here, because our main intention is to calculate the pressure drop later. So we need, we know that the pressure drop happened in the valve. So we need to identify where is the valve is. So first, let's focus on the valve first. So the first point is not about the valve. The second point, it says that an isolation valve from the vessels. So it says that for any vessel, we should have one valve. So we have a valve for this tank, and we also have valve for this tank number 2. So let's move on to the pump. So the third point, we have 2 isolation valve and 1 check valve for the pump. So which means for this pump, we also have another isolation valve, and we have a check valve here. So we also have orifice plate for measurement. So for flow measurement, so we have an orifice plate, and we also have control valve. Let me remove this part first because I don't have enough space. So just to recap, this is isolation valve. Isolation. And this is also isolation valve. And we have this as our check valve. And this as our orifice. So we are at the point number 4. And then point number 5, we have a control valve. So here we have a control valve. And for the control valve, we also have isolation valve for this. And then the next point is about 3 pipe bands. Later we take that into consideration. And we have isolation valve for this discharge vessel. So basically we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 valve and also orifice based on this guideline. Based on this guideline, so all of this would induce the head losses. So now the first part is focused on where the valve is placed or where the valve should exist in order to transport liquid from point A to point B. So now let's focus on the head losses. So let me change this one into red pen. First, we have a sudden contraction from the feed vessel. So we have sudden contraction, and we have from the valve, all of this valve, whether it's isolation or control valve, and also this orifice. And we, for any liquid transmission, typically we have 3 pipe bands from the chain for the change in direction. So let's say we have +3 bands that induce the head losses, and we also have a sudden expansion here. Sudden expansion. So which means our head loss so we have from 9 valve and orifice. So we have +1 contraction, +1 expansion, and +3 bands. So where else is the pressure loss? We actually have throughout the pipeline, because we have the fluid. So let's say this is our pipeline. So the surface or the wall of this pipe will also induce the pressure drop. We should take that into consideration also. So based on the pipe length. So which means we have another one for the total pipe length. So this is assuming this is a only a straight line. So what happened? So what happened is this is fed, or this tank is located in elevated position. We should also take consideration based on the elevation. So now our total head loss is also induced by the elevation. So for a transport liquid from tank A to tank B in typical chemical process, this is where the head loss or our pressure drop come that cause the pressure drop. So which means we need to supply our work to overcome this head loss. To overcome head loss. So if you look into the slides here, over here there should be there should be one, there should be another one that represent a control valve, and plus another two that represent the isolation. So is that clear? Okay, before we take a break, so why this 9 valve? So we have isolation valve. So it meant to isolate the specific equipment. So in what situation we use this? Basically during or for maintenance purposes. For example, for this pump, so if this pump need to be servicing, so we need to use this isolation valve here so that we can close up this valve, this two valve, and then we can take the pump out for servicing. Same goes for this when there is this tank need a maintenance. Let's say there is a leaking somewhere, so we need to isolate this tank from the process by close this isolation valve so that it would be no flow. The second one is on the check valve. So the check valve, or we call it as one-way valve, which is located at this part. So we use the check valve. We use the check valve to make sure that it does not goes back back into the pump. We also have orifice plate to measure the flow rate, and we also have a control valve. The control valve is to change the flow rate. To change the flow rate according to our process requirement. So that's it for the pressure drop. Any question for pressure drop? So if you see me looking like this, I'm referring to my second screen here so that I can see how you're doing. So good. Yeah, sorry, my handwriting is not that perfect. So hopefully you can still read it. Okay. So if no question, so let's take a quick break. A quick break is 5 minutes break. So we'll continue at 8:50 a.m. Is that okay?
Okay, sir.
Okay, so we'll continue at 8:50 a.m. Then we'll continue with today's lessons, focusing on the pressure drop calculation. All right, thank you. Okay, so let us continue with the head loss calculation. Head loss calculation. For a liquid system, when we have involved liquid, we need to assume that this fluid is incompressible, which means whatever when there is pressure or pressure drop happen, the volume of the fluid is maintained the same. So for this, the delta P over rho G, the delta P over rho G is equal to the summation of head loss plus delta Z. Delta Z here would represent the changes in elevation, which if we still recall the previous example, all of this head loss, it's by all these 9 valves, 1 contraction, 1 expansion, 3 bands pipe, and also the pipe length. And we also have this 1 elevation here. So first, let's focus the breakdown into all of these head losses here. So the first is the head loss for a straight pipe. So throughout this pipe length here, this is the calculation for the head loss. First, the head loss is equal to 2CF. The CF would represent a friction factor, the length of the pipe, the velocity of the liquid inside the pipe, and also the T here, the internal diameter G. So the challenge here is how can we calculate the friction factor? So to calculate the friction factor, we need to understand the flow behavior of the liquid. So to understand the flow behavior, we need first to calculate this Reynolds number. So for different flow behavior, we have different friction factor to be friction factor equation to be used. So that is for the straight pipes. That is for the smooth pipe actually. So if we have a rough pipe, so we will use a different CF factor where we need to take consideration of our surface roughness. Surface roughness. Now let's focus on the head loss in the pipe fitting based on this valve here, valve and also the bands. So for the head loss in the fitting through pipe and through the valve and orifice, we have CL, our loss coefficient, which is unitless, multiplied by velocity squared over 2G. So our CL here is depending on the specific valve and also the, because of the geometry of the valve, we would have different loss coefficient. So that goes into 1 by 1. So let's say if we have the band, pipe band. So if the Reynolds number is less than 1100, we are to use this equation in order to calculate the loss coefficient. Whereas if it's turbulence, when the RE is more than 1100, we straightly use 0.8 here. We also have globe valve. This globe valve is for the control valve. For control valve, we have based on the Reynolds number also. And we also, this is represented when it is laminar flow. And when we have a turbulent flow, we can directly take CL of 6 or 9, depending on the type of globe valve. And when we have a globe valve, we are to assume that it is 50% open. 50% open, or If it is not stated, we are to assume that it is 50% open. And for this globe valve, we have additional correction factor, which is we need to take account into this alpha here. So let's say the opening is 50%, our alpha value is 0.5, and it needs to be the power of 0.5 when we have a composite seat globe valve. For plug this, we have the opening to the power of 1.84. And we also have the gate valve, all of this equation. And later, once we do, we need to goes back into this table in order to identify this loss coefficient. So we have take consideration of this pipe length here together with this bend and the valve and also the orifice. So now let's focus on the contraction and expansion. So for contraction, we have another equation that represent here. Expansion also here. And we also have in terms of this orifice plates. And for this, keep in mind that, let me see if I can find it. Okay, here. So for this sudden contraction, we need to take consideration of the pipe diameter so that we can calculate the area area of the pipe that caused the sudden contraction or expansion. Same goes when we have the orifice plate, because it's also limits our flow here just to measure the flow rate. So we also need to take consideration into this area. So for orifice plate, refer to this equation. And we also have a new term, which is CD squared here. So what is CD squared? This is another correction factor. So typically we use 0.62 for preliminary design. And when we don't have the information related to the pipe velocity, what can we do is we can use assumption to measure the fluid velocity, and we can also use this commonly standard pipe size in order to assist us in the head loss calculation. For the time being, it may not seems to have much sense. So later when we do the example, so we'll know when to use this. So let's go straight into this example. Let's go straight into this example. So we have water is to be pumped between two vessels separated by an estimated distance of 30 meters under action of flow control. So an increase in elevation of 5 meters is also estimated. The flow rate of water is 100 meter cube per hour with viscosity of 0.8 millinewton or centipoise here. And this is the liquid density. So we are to estimate the pressure drop required by the pump. So first, for any engineering solution, first is to list all the known variables here. So first, we have the length of 30 meters. We have the change in elevation by 5 meters. And we have flow rate of water, F equal to 100 meter cube per hour. And we have the viscosity equal to 0.8 center poise, and we have the density equal to 993 kilogram per meter cube. So we are to estimate what is the pressure drop in order to transport liquid from tank 1 to tank 2. So this is all the information that we have. And before we can calculate, let's goes back into our previous example to identify what kind of valve or fitting is happening here. So let's get back into this figure. So first we have isolation valve to isolate these two tanks. So we have 1, 2, 3, 4, 5, and 6. So we have 6 isolation valve. We have 1 check valve. And we have 1 orifice to measure the flow rate. We have 1 orifice, and we have 1 globe valve for control valve. So we have 1 control valve. So this is for the valve. So let's see. So let's see here. So for the isolation valve, typically we'll use a gate valve. So for check valve, we already have this. And for control valve, we'll be using globe valve here. So that is the valve associated with this process. And we also have 1 orifice. Well, I already include 1 orifice here. And we have contraction and expansion. So we have 1 contraction, 1 expansion. And by rule of thumb, or by this previous guideline here, so we would have 3 pipe bands when we use for the transport. So we are going to include this here, 3 pipe band. So this is the additional information based on our understanding or based on the guideline to identify where does the head loss occurs. So we have all of this. So let's check into our equation here to see what are more information that we need. So first, I forget to include, we have 1 in terms of pipe length. And we have another one from the elevation. So all of this will contribute to delta P over rho G equal to summation of head loss plus the delta Z. So first, let's have a look. We need to calculate the CL of each of the fitting. So before we need to calculate the CL, we need to calculate the Reynolds number, which given by this equation, density, inner diameter, velocity, together with the viscosity. So we only given our flow meter, our flow rate, 100 meter cube per hour, and we need to use this velocity in order for us to calculate the Reynolds number. So that's when we need to assume the velocity, because we cannot calculate the velocity without identify the geometry of our flow rate. So just to recap what I would do, because we don't have the, so we only given with flow rate F. So because we don't have the area, we are going to assume the velocity of the fluid. So once I able to assume the velocity, I can calculate the Reynolds number. So once I calculate Reynolds number, so I can calculate the loss coefficient. Then I can calculate the head loss. So first, we are given with 100 meter cube per hour here. 100 meter cube per hour. And our density is, our viscosity is 0.8. So let's use this table in order to estimate our fluid velocity. So our viscosity is 0.8. So it is a low viscosity liquid. So we can assume the velocity 1 until 2. So let's assume our velocity equal to 2 meter per second. So once we assume 2 meter per second, we have Q or flow rate F would be equal to the velocity multiplied by the area, meter over square, multiplied by the area. So flow equal to velocity multiplied by cross-sectional area. So from this, we can calculate the area, which is equal to F over V, which is 100 meter cube per hour over 2 meter per second. So when we do the correction in terms of the units here, so we have the area equal to 0.01389, which is our area is equal to pi r square or pi d square over 4. So from this, calculating this, we would get our diameter of 0.133 meter. So from this, just to recap, what is the step? So from the viscosity of our fluid, we assume the velocity. So from the assumed velocity, we can calculate the pipe cross-sectional area. So from this, we can estimate the pipe diameter. So now our pipe diameter is 0.133. We are to round it up to the largest standard pipe diameter. So now our diameter is 133. So this is equal to 133 millimeter. So which means if we were to round up, we need to take this number as our pipe diameter. So use a standard pipe. Now our diameter is 0.154 meter based on this table. So after we have this, then we can recalculate our velocity. So we can have our actual velocity is 1.49 meter per second. So once we have this velocity, then we can calculate the Reynolds number, which we will get 2.85 10 to the power of 5. So, and then we are to substitute into all of this equation earlier. So once we have the Reynolds number, then we goes back into the previous slides to calculate the CL of each. So once we able to calculate that, once we combine, we can calculate the total of pressure drop inside. The total pressure drop in order to transport fluid from tank 1 into tank 2. So the detail of the calculation, you can refer to the slides later. But what is the output from this exercise is we want to calculate this delta P. So from this, we have delta P equal to 1.87 10 to the power of 5 Pascal, which is also equal to 0.187 10 to the power of 6 Pascal, which is 1, 2, 3. So 187 kilopascal. So this is the amount of the pressure drop along in order to transport point 1 to point 2. So which means we need to have, when transporting the fluid here, we need to make sure that the work we supply here can overcome the outlet pressure here. The outlet pressure is more than, so let's say if this is 100 kilopascal, the pressure 2 will be equal to P1 plus delta P. So 100 plus 187. So the outlet pressure must be 287 kilopascal for this pump to work. Okay. So bear with me for a while. Bear with me for a while before we take a break. So ultimately now we already managed to identify the pressure drop in our process. Now we need to calculate what is the pump power required for this. So the type of pumps, later you can study it on your own. Let's focus on how can we calculate the pump power. So now we know we need to overcome this. So our work is equal to F delta P over efficiency, where F is our flow rate, delta P is the pressure drop, and is the efficiency, in which we can estimate based on this equation in the slides. So this equation is useful to get the first estimates. So once we just to recap, once we get the pressure drop, then we can estimate what is the pump power required for this process. So there is also example in the slides, just to highlight how we can use this. So once we're able to calculate the pump power, in the end, we can calculate how much cost is required. So let's take this example. We have centrifugal pump to deliver 100 meter cube of water, and we are to increase the pressure of 5 bar, which means, so let's say this is from 1 bar, we need to increase by 5 bar, so that we have the outlet here by 6 bar. So the efficiency of this electric motor here is 90%. So from electricity, before it can convert into works, the efficiency is 90%. So calculate the work required for this and estimate the annual cost of power. So first, we are to assume, we are to calculate the pump efficiency by using the flow rate here. So from this, we can get the efficiency equal to 0.78, 78% here. So, and then we calculate the work from this equation by take also consideration of pump efficiency together with electric motor efficiency. So now we're able to get 19.8 kilowatt. This pump required 19.8 kilowatt. From 19.8 kilowatt, then we can calculate with the time of operation together with the electricity cost for the process. Okay. So this is quite a lengthy calculation. And so make sure when there is involved a lengthy calculation, you will have a tendency to make a wrong calculation when doing the exercise. So make sure you practice based on this example here, so that we can able to minimize the minor mistakes here. So the next part is about compression, but I believe we are due for a break so that we can unsaturate our mind. So let's take another break. So now it's 9:20. So we'll continue at 9:25 a.m. while the focus is on the compressor. Okay, so we'll come back in 5 minutes. Okay, so let us continue with the next part of our lecture, focusing on compressor. So for compressor, I'm going to skip the first part of the compressor, focusing on the type of compressor. So I believe you can do your self-learning on this part. So when we take consideration into compressor, so let me draw the compressor here. So we have inlet and outlet, and we have the work in order to increase the pressure or to transport the gas from inlet to outlet. So first, let's focus on the compressor. So we want to increase pressure from P1 until pressure of P2. So that is the role of compressor. So how can we get the maximum compression ratio? So in compressor, one thing that we need to take into consideration first is compression ratio, which is the ratio between pressure outlet over pressure inlet. So the next one is the ratio of heat capacity of the gas. So we have the term gamma here, which is Cp over Cv. So this gamma is depending on type of gas. And last is about inlet temperature here. So about the inlet temperature. So all of these three factors would determine on how compressor should be run. So first, let's focus on this term, inlet temperature. So why is it necessary for this? So for inlet temperature, so just to highlight on this, so let's recall our ideal gas law. Ideal gas law, we have PV equal to N RT. So what can we address from this is the correlation between pressure and also temperature. Pressure and temperature, which means if we are going to increase the pressure of our gas here by compressor, the temperature of our gas would also increase. So the question raises, how high the temperature can compressor tolerate? So how high the temperature? So we need to focus on this. Let's focus on this statement. How high the temperature can compressor tolerate? So let's have this compressor figure here. So in compressor, we would have a motor that is rotating. So when you have something rotating or some mechanical action going on, there would be a friction. The most obvious one is when you put your hand together, you try to rub it in together. You can feel that the temperature at the palm of your hand increase. So this rotating, because of the friction, you would have temperature increase. So in order to minimize the friction, we need to use lubricant. So we need to use lubricant to minimize the friction so that the temperature would not increase excessively.